So far, we have considered estimation using a random sample, which is also called an IID sample, from the population of interest. This is actually an idealized situation because in practice, we rarely have exact IID sampling. There can be many different issues that will make the sample not IID. And here are the three issues that we're going to talk about today. One is finite population. The second is sample selection. And the third is complicated advanced sampling technique. Complicated sampling technique could result in samples that are not IID samples. Let's start with finite population. So in previous videos, we say that a population is a distribution F. And that population is actually an infinite population because it's the distribution F typically has infinite number of support points. And when you draw from an infinite population, there is no distinction of sampling with or without replacement. But when the population is finite, for example, when the population is the US households, there are many US households, say maybe 90 million or so, but still that is a finite number. When you sample from a finite population, the two sampling techniques, these two sampling techniques will be different. One is sampling with replacement, and the other is sampling without replacement. Sampling with replacement is after you draw an individual from the population and observe his or her variable value, you put him or her back to the population. Pretend that you didn't draw that individual, so you forget about him or her. Put him back to the population when you take the second draw. And then after you take the second draw, you put the second draw back into the population before you draw the third individual, and so on and so forth. So when you do sampling with replacement, the sample you get is guaranteed to be IID because each time you take the random draw, the population you face is exactly the same. So this will give you an IID sample, but it has one drawback, that is, it is possible that you draw the same individual twice and interview this person twice, and that's kind of weird and maybe even a waste of energy. Or even more times. And when you sample without replacements, after you draw an individual and observe the individual's variable values, you do not put that individual back to the population. So you draw the subsequent individuals from the population with the individuals already drawn removed. That clearly doesn't give you an exactly IID sample. Doesn't exactly result in an IID sample. That's because your population is finite. After removing individuals that you have observed, the remaining population is different from the population you started with. So sampling without replacement doesn't give you an IID sample. the individual draws that you have taken are drawn from different populations, and they're also interdependent, because suppose that the population only has one individual who earns like, so suppose that the first time you draw the individual, you got the individual who earned the highest income. Then when you draw the second individual, the individual with the highest income had already been drawn, and the population left will have a lower income distribution. So what the second draw will be depends on what the first draw is. So the individuals in your sample, when you do sampling without replacement, will be dependent, and they will be drawn from different populations. So the sample you obtain is not exactly IID, but it has the advantage of never drawing the same individual twice. And because of this second feature, the sampling without replacement is actually the most common kind of sampling. So it's much, much more common than sampling with replacement. But typically, we don't worry about this very much. We don't worry about the issue of not getting an IID sample exactly very much. The reason is typically we think that the population is large enough. When the population is so large, whether you replace or not doesn't affect things very much. Whether replace the individual already drawn or not doesn't affect the remaining population much, and doesn't create all that much dependence across individuals. So even though there is this distinction, this is not a huge issue in most scenarios, not big issue. When population is large. So that is why in practice, even though most data sets are sampling without replacement, we still treat it as a random sample. The second issue is more serious. That's the sample selection issue. So what is the sample selection issue? Basically, the sample selection issue is the target is occurs when the target population, that's the population that you are interested in, the population you want to target, that population is different from the population that your sample is drawn from. If your sample is not drawn from your target population, then the estimate coming from your sample will not estimate the right population quantity. Right? So the estimate coming from the sample will estimate the quantity from the population the sample is drawn from very well, but that is, if that is not your target population, then you are missing your target. This is a very common and serious issue, and we should always be aware of it. Just to give you a concrete idea, let's consider this example. In this example, let's say that the parameter that we want to estimate is the proportion of people in Madison, of all people in Madison, proportion of all people in Madison who have been infected by SARS-CoV-2. So the population that we target, we want to learn about is the whole population of Madison. So target population of Madison. So we want to know the distribution of infection in the whole population of Madison. But since not everybody in Madison have been tested, we do not know the proportion of people in Madison who have been infected. And can we use theta hat, that is the positive rate among all tested, number of people who have been tested positive divided by the number of people who have been tested? Is that a good estimate for theta? Well, to answer that question, you need to think about the question whether the people who have been tested is a random sample from your target population. Well, there are many reasons to believe that this sample is not a random sample from the target population. If you think about when people will actually go through the trouble to do the test, most of the time is when they have been in close contact with someone who have been tested positive, or when they experience symptoms that makes them think that they might have the virus, so they go to get test. And other people who have not been in close contact with someone who have been tested positive or have not experienced any symptom will simply not go through the trouble. So that sample is probably for a population is drawn from the population from a population or is that is more likely to have been infected than the general population. So this is a selected sample, selected based on whether the person believes that he or she has a higher probability of having been infected by the virus. So one remedy to this selection problem might be to randomly select people from the community and then encourage them to take the test or force them to take the test. And of course, you might say this is not ethical. It's not possible politically or legally to do this, to randomly draw a sample from the population and force them to take the COVID-19 test. So there might be other ways around it. For example, when hospital admit patients during the pandemic, when hospital do routine surgery that are not related to COVID-19 at all, some other kind of surgery, whenever they admit someone to the hospital to do a surgery that's not related to COVID-19 at all, they require the patient to take the COVID-19 test. So the people who go to a hospital to do a surgery, that is not a random sample from the population either. However, that might be from a population that has similar infection rate as the general population, because there is no reason to believe that people who there is fewer reason to believe that people who go to a hospital to do a surgery that's not related to COVID-19 at all, it has a higher or lower rate of infection than the general population. So that could be a remedy. If you believe that the population who go to the hospital to do a surgery not related to COVID-19 doesn't have a higher or lower proportion of infection than the general population, then that would give you a better estimate for theta, better estimator than theta than this one. Now I want to share with you an interesting observation that I have about the presidential election that's going to happen in November. So I am Chinese living in the United States, so I have both a Facebook account and a WeChat account. I observed that my Facebook friends believe that Biden will win the election. So they attach very high probability for Biden win. On the other hand, my WeChat friends attach very high probability to a Trump win. They think that Biden has zero chance of winning the election. So why is there such a difference? You can consider the prediction, their predictions, my Facebook friends' prediction and my WeChat friends' prediction. Both are estimators for the support rate of the two presidential candidates. Clearly, there is only one true support rate in the population of the United States voters, but there can be many estimators. The estimator of my Facebook friends indicates that there is overwhelming support for Biden. Well, the estimator of my WeChat friends indicate that there is an overwhelming support for Trump. Why are they so different? Well, I do not know why they are so different. My hunch is that my Facebook friends are mostly university professors who are more liberal, and they have friends who are more liberal as well. So what they observe is a group of people who are much more liberal than the general US population. And among this more liberal population, clearly the support rate of Biden is much higher. On the other hand, my WeChat friends, among those who are in the United States, are mostly Chinese Americans. And unfortunately, Chinese Americans are much more conservative and they're more tolerant of whatever the president does. So my WeChat friends has other WeChat friends who are more conservative. So their observed sample is from a population that is more conservative. And therefore, they observe a higher approval rating for the president. And that's what they base their prediction on. So that's my analysis of these two different, two opposing views of the upcoming election. And I believe that's the difference is because their observations are both selected samples of the population, and they're selected from the two ends of the spectrum. The third sampling issue that I want to briefly mention is the stratified and convenience sampling. Stratified sampling is a type of sampling technique, and convenience sampling is another sampling technique. They are used for their reasons, but they will break the random sampling assumption. For example, the stratified sampling. So what is stratified sampling? In stratified sampling, you first stratify or split the population into subpopulations according to some observable characteristics. For example, in this population, there are square people and there are circle people. So you first stratify the population into the square people and the circle people. And let's say you want to randomly sample 25% of the population. Then after the stratification, you draw 25% from the square population and form your squared sample. And from the circle population, you draw 25% randomly, and that form your circle sample. Then you put all of them together, that will be the whole sample. This sample is not an IID sample because this part of the sample and that part of the sample are drawn from different distributions. So IID sampling does fail for stratified sampling. And the second type of sampling technique is convenience sampling. That's also very useful in practice. It's used a lot. So I will give you a scenario where this is very useful. Suppose that you want to study a rural population. You want to study, say, their income, their labor input, and their, say, health condition, and so on. You want to study the rural population. But relative to the urban population, the rural population are more scattered, more spread out geographically. Let's say that the rural population are divided into many villages. So this square village, this circle village, this triangle village, and there are many other villages. And the villages are spread out in a very large geographical area. If you do a simple random sampling, that sampling might sample one individual from the square village, maybe two from the triangle village, maybe one from the circle village, and so on. Then in order to interview all of these individuals, you have to travel to all of these villages. That involves a lot of transportation cost. So that is not very convenient. So for this kind of problems, one commonly used technique is to randomly draw a village. And then you travel to that village. Once you have traveled to that village, you interview everybody in that village. So that's called convenience sampling. Convenience sampling also breaks the random sampling assumption. It causes IID to fail because the individuals that are surveyed in the same village, they are dependent. And because they are dependent, so this sample fails the IID assumption. So these are advanced sampling techniques that are useful for their own purposes, but we need to keep in mind that they fail the IID assumption. We might touch upon some solutions to these problems later on in this course if we have time, or not. If we don't, then maybe I think you will learn about them in future courses.